1901, far beneath the surface of the Mediterranean Sea, a group of divers descended toward the remains of an ancient ship. They expected statues, coins, perhaps a few pieces of pottery. Instead, they found something nobody understood: a corroded lump of bronze. Buried among the wreckage was a machine that would force archaeologists to rethink what ancient engineers were capable of. At first, it looked almost worthless, a broken, greenish mass of corroded bronze. Nothing about it suggested a technological revolution, but inside that damaged object, something extraordinary was hiding. Gears, dozens of them. The surviving mechanism is known to contain at least 30 bronze gear wheels, along with astronomical inscriptions. Then came the moment that changed everything. Researchers began looking beneath the corrosion, and there it was, a tiny bronze gear, then another and another, wheels within wheels, connected by an intricate mechanical system. This wasn't a simple ornament, it was a machine. But what was the machine actually doing? The answer was far stranger than anyone expected. Turn a single input, and the gears could model cycles in the heavens. The moon, the sun, calendars, and eclipses. More than 2,000 years ago, someone had created a mechanical representation of the sky. But the most remarkable part may have been the moon. The moon does not move across the sky at a perfectly constant speed. Ancient Greek astronomers understood this irregular motion, and somehow the mechanism reproduced it mechanically. No computer, no electricity, no silicon, just bronze gears, mathematics, and an astonishing understanding of the sky. And then came the eclipses. Hidden within the mechanism was a system based on astronomical cycles that could indicate when solar and lunar eclipses would occur. To the people who built it, the heavens weren't simply something to watch. They could be calculated, predicted, translated into motion by metal. And this is where the mystery becomes bigger. The Antikythera Mechanism wasn't simply impressive. Researchers have described it as technically more complex than any known device for at least a millennium afterward. So, where did this knowledge come from? Who taught these engineers to build machines like this? And perhaps the most important question, what else did the ancient world know that has been lost? The Antikythera Mechanism proves something extraordinary. Ancient technology was not always crude. Sometimes it was astonishingly sophisticated. But the mechanism raises an even stranger possibility. What if this wasn't an isolated achievement? What if other technologies existed? Technologies whose secrets disappeared with the civilizations that created them? Our next discovery takes us from bronze gears to a material that has survived almost 2,000 years. And somehow, it may be able to heal itself. 2,000 years ago, the Roman Empire was building cities that would outlive the empire itself. Roads, bridges, harbors, aqueducts, massive domes. And beneath all of them was a material we thought we understood: concrete. But then scientists began asking a disturbing question. Why was some Roman concrete still surviving after nearly 2,000 years? Look closely at the ruins of Rome, and something becomes difficult to explain. Structures built almost 2,000 years ago are still standing. The Pantheon, Roman harbors, aqueducts, walls, and foundations. They survived centuries of weather, earthquakes, flooding, and the collapse of the civilization that built them. So what did the Romans know about concrete that we have forgotten? But surviving isn't the same as healing. Concrete cracks, water enters, the damage spreads. Eventually, the structure weakens. That's one reason modern engineers spend enormous amounts of money repairing concrete. But researchers examining Roman concrete noticed something strange. Tiny white fragments hidden inside the ancient material. For years, these white chunks were largely treated as imperfections, perhaps sloppy mixing, perhaps poor quality material. But one researcher wasn't convinced. Why would Roman builders, who had spent generations perfecting their construction techniques, deliberately leave what appeared to be flaws inside their concrete? What if they weren't flaws at all? The investigation led somewhere unexpected. The Romans weren't simply mixing ordinary lime with volcanic ash. evidence suggested something more unusual. They may have been mixing quicklime directly with other ingredients, producing an intense chemical reaction. Heat was generated inside the mixture, and that heat changed the chemistry of the concrete, a technique researchers call hot mixing. And then came the experiment. Researchers created concrete using the ancient technique. They deliberately cracked it, and then they introduced water. At first, nothing appeared to happen, but inside the crack, the chemistry had already begun. The lime inside the concrete could react with water. Calcium-rich material dissolved, moved through the fracture, and recrystallized. Slowly, the gap began to fill. The crack that had opened the door to destruction was becoming sealed again. In laboratory testing reported by the researchers, cracks in hot mix samples healed within about 2 weeks, while comparable samples without quicklime did not. The ancient material wasn't alive. It wasn't magic. It was chemistry. But chemistry that ancient builders had somehow learned control. But there was still a problem. How could scientists be certain this technique was actually used by Roman builders? Then, archaeology provided something extraordinary, a construction site frozen in time. Pompeii, when Mount Vesuvius erupted in the year 79, it buried an active Roman building site. Almost 2,000 years later, researchers could examine the materials almost exactly where ancient workers had left them. Pompeii had preserved something almost impossible to find, not just a finished building, but the construction process itself. Piles of raw materials, a wall being built, completed sections, repairs. It was as if the eruption had pressed pause and left scientists a snapshot of Roman engineering, and the evidence pointed toward the same unusual technique, hot mixing. So was Roman concrete actually a form of ancient magic? No. The answer is far more impressive. They understood materials. They understood heat. They understood volcanic ash. They understood lime. And through generations of experimentation, they developed a construction technology whose chemistry we are only now beginning to fully appreciate. The Romans didn't have modern laboratories. They didn't have electron microscopes. They didn't have computers. Yet they discovered something modern engineers are still trying to reproduce. The Romans didn't build concrete that could think. They built concrete that could respond. And that distinction matters, because sometimes the most advanced technology isn't the one with the most complicated machine. It's the one that quietly solves a problem before anyone realizes the problem exists. But the Romans weren't the only ancient civilization experimenting with technology that seemed strangely familiar. Somewhere else, an ancient vessel was found containing metal, acid, and a mystery. Some researchers wonder whether it could have produced something humanity supposedly didn't discover until thousands of years later. Electricity. Was the Baghdad Battery really a battery? Or have we misunderstood one of archaeology's strangest objects? Somewhere in ancient Iraq, more than 2,000 years ago, someone made a strange object. It wasn't a weapon. It wasn't jewelry. It wasn't a statue. It was a simple clay vessel. Inside it was a copper cylinder, and inside the cylinder, an iron rod. For decades, archaeologists and scientists have argued over one extraordinary possibility. Could this have been an ancient battery? When archaeologists uncovered these vessels near Baghdad, they had no obvious explanation for them. They were small, simple, almost ordinary, but inside was a combination that caught the attention of scientists. 2 different metals, separated by a liquid-holding container, a design that sounded surprisingly familiar. The idea was surprisingly simple. Place the copper cylinder inside the clay vessel, insert the iron rod, add an acidic liquid, such as vinegar or another suitable electrolyte, and something remarkable happens. A chemical reaction can produce an electrical potential between the 2 metals, not enough to power a city, not even close, but potentially enough to demonstrate something astonishing. Electricity. Modern reconstructions have shown that a vessel built on this basic principle can generate a small voltage. But here's where the story becomes complicated. Being able to generate electricity doesn't prove that the ancient people who built the vessel intended it to. And that's the problem. We have the object. We can reproduce the electrical effect. But we don't have the ancient instruction manual. In the 20th century, the Baghdad Battery interpretation captured the imagination of the public. What if ancient engineers had discovered electrochemistry centuries before modern science? What if electricity was invented but rediscovered? The idea was irresistible. But archaeology doesn't work on what is irresistible. It works on evidence. And there is a serious problem with the battery theory. What was it for? Where are the wires? Where are the electrical devices? Where are the workshops filled with similar cells? Where is the evidence that anyone actually used electricity? Archaeologists haven't found a clear answer. And without that evidence, calling the object a battery may be going much further than the evidence allows. So perhaps it wasn't a battery. The vessel could have served another purpose entirely. Storage, ritual, a container for scrolls or organic material, or something we haven't yet considered. The problem is that the artifact itself doesn't tell us what its maker intended. And that's what makes this mystery so difficult. Yet something important remains. The mystery does not require the object to be a battery, because the chemistry itself is real. Put two suitable metals into an electrolyte, and chemical reactions can create an electrical potential. Ancient people didn't need to understand electrons to observe strange effects. They only needed to experiment. And perhaps this is the more interesting possibility. Ancient technology didn't always begin with a complete understanding of science. Sometimes it began with curiosity. Mix this, heat that, combine these metals. Try again, watch what happens. Repeat, improve, and eventually knowledge becomes technology. So, was the Baghdad Battery really a battery? We don't know, and that's important. Because the most fascinating ancient mysteries aren't always the ones with spectacular answers. Sometimes they're the ones where the evidence leaves the door open. The object may have produced electricity, but whether anyone intended it to remains uncertain. And that uncertainty leads us somewhere even more interesting. But there's something we can say with confidence. Ancient civilizations were extraordinarily inventive. They experimented with materials. They developed sophisticated metallurgy. They understood chemical processes without knowing modern chemistry. They built machines without computers. And sometimes, they stumbled onto principles that modern science would later explain. The Baghdad Battery may not prove that ancient people had electricity, but it does prove something else. We still don't understand everything they were trying to do. The strange vessel from Iraq leaves us with a question, not did ancient people have electricity, but something much more profound. How much can civilization discover without understanding the science behind what it has discovered? Because our next technology doesn't involve electricity. It doesn't involve bronze gears. It doesn't involve concrete. It involves something far more primitive, water. And ancient engineers learned how to make it move without pumps, without electricity, without engines, using nothing more than pressure, gravity, and an astonishing understanding of engineering. Water has a rule. It flows downhill. Gravity pulls it toward the lowest point. And yet, thousands of years ago, ancient engineers discovered ways to make water move where gravity said it shouldn't. Up, across valleys, through tunnels, into cities, and onto fields. They had no electric pumps, no diesel engines, no modern machinery. So how did they make water climb? Water movement. Imagine watching this without knowing the mathematics behind it. You turn the handle and water rises again and again with every rotation. Another column of water is lifted. No engine, no electricity, just geometry, motion, and gravity being temporarily outsmarted. And here's where the story gets complicated. We call it the Archimedes screw. But Archimedes may not have been the first person to use the idea. Evidence points to water screw technology in ancient Egypt around the 3rd century BC. The Greeks later adopted the device. Archimedes became strongly associated with it. So perhaps the Real story isn't about one genius inventing a machine. Perhaps it was knowledge moving between civilizations. But the screw wasn't the only solution. Long before it, Egyptian farmers were already lifting water with an astonishingly simple machine: a long wooden beam, a counterweight, a bucket. Pull the bucket down, and water comes up. Release it, and the counterweight resets the machine. Again and again, an ancient mechanical advantage, built almost entirely from wood. But lifting water was only half the problem. Ancient cities needed enormous amounts of it: drinking, farming, bathing, industry, sewage, and the water wasn't always nearby. So engineers did something even more extraordinary. They moved entire rivers. Without engines, the secret wasn't magic. It was slow, tiny differences in elevation, carefully calculated over enormous distances, allowed gravity to do the work. Water entered at a higher point. The channel descended almost imperceptibly, and gravity carried the water toward the city, sometimes across valleys, sometimes through mountains, and sometimes underground. But sometimes there was no convenient valley, no easy route, no way around the mountain. So ancient engineers went through it. They measured, they calculated, and they began cutting into solid rock from opposite sides with primitive tools. They attempted something that would challenge engineers even today. Meet underground. On the Greek island of Samos, ancient engineers built a tunnel more than a kilometer long through a mountain. It wasn't simply a hole in the rock. It was part of a water supply system, and the tunnel was excavated from both ends. The engineering challenge was extraordinary because if the calculations were wrong, the two teams would never meet. Then, somewhere deep beneath the mountain, the sound changed. One team heard the other. Stone broke away, and suddenly there were faces on the other side. Two groups who had started from opposite directions had found each other underground. The mountain had been crossed, and water could now pass through. And perhaps that's the secret we've been missing. Ancient technology wasn't always about mysterious machines. Sometimes the technology was the ability to understand nature: gravity, pressure, water, geometry, balance, materials. Ancient engineers didn't need to defeat these forces. They learned how to work with them. But water was only one part of the ancient engineering revolution, because once humans learned how to control water, they began asking another question. What else could they make move? What if water could turn a wheel? What if a wheel could produce mechanical power? What if pressure could move machines? What if steam could become motion? And suddenly, we arrive at something that sounds almost impossible. A machine powered by steam, built nearly 2,000 years ago. The ancients didn't have electric pumps. They didn't need them. They used gravity, pressure, geometry, and simple machines to move millions of liters of water. But then, something even stranger appeared. A Greek engineer watched steam escaping from heated water and realized something profound. Steam could make things move, not someday, not in theory. Right then, more than 1,000 years before the Industrial Revolution, an ancient machine began to spin. And if the idea had been developed differently, could history have entered the age of steam almost 2,000 years early? Alexandria, nearly 2,000 years ago, in one of the intellectual centers of the ancient world, engineers were experimenting with something invisible, something that could not be held, something that disappeared into the air: steam. And one engineer was about to discover that steam could do something extraordinary. It could make a machine move. The experiment began simply. Heat water. The water boils. Steam rises. To most people, that's all it is. But Hero saw something different. He saw pressure. He saw movement. And he wondered, what happens if you trap the steam? Hero constructed a hollow metal sphere. Two bent tubes extended from opposite sides. The sphere was connected to a vessel of boiling water. At first, nothing happened. Then the water became hotter. Pressure began building. Steam entered the sphere. And suddenly, the sphere began to rotate. Steam escaped through the curved tubes. The escaping steam pushed against the surrounding air, and the sphere reacted, slowly at first, then faster and faster. A machine, powered by steam, was spinning. Nearly 2,000 years before the Industrial Revolution, What was happening was simple but profound. Steam rushed through the pipes. It escaped through angled openings. The change in momentum produced a reaction force, and that force made the sphere rotate. Hero had created something remarkably close to a primitive reaction turbine. But there was a problem. It wasn't practical. The machine could spin, but spinning wasn't enough. It couldn't efficiently power a factory. It couldn't transport goods. It couldn't drive machinery for hours. It was a demonstration of an extraordinary principle rather than the beginning of an industrial revolution. And this raises one of the biggest questions in the entire story. If the principle existed, why didn't civilization follow it? The Industrial Revolution required more than steam. It needed precision manufacturing, reliable boilers, strong materials, fuel supplies, machine tools, investment, transportation, and an economy capable of turning mechanical ideas into mass production. Hero had discovered something remarkable, but he didn't have the industrial ecosystem required to transform it. And steam wasn't Hero's only fascination. His writings described devices that use pressure, air, water, weights, and mechanical motion. Some could produce automatic movement. Some could manipulate doors. Some could create theatrical effects. Ancient engineering was becoming something new, machines that appear to act by themselves. Hero's surviving works describe a wide range of pneumatic, hydraulic, and mechanical devices, including automated theatrical mechanisms. Imagine walking into an ancient temple. A priest lights a fire. Nothing appears to happen. Then, the temperature rises. Air expands. Pressure changes. Water moves. A hidden mechanism activates, and enormous doors begin to open. To an ancient observer, it might have looked like a miracle, but behind the illusion was engineering. To the crowd, it was supernatural. To the engineer, it was physics. Heat, pressure, air, water, gravity, mechanical advantage. The machine didn't break the laws of nature. It exploited them. It had sophisticated mechanical knowledge. It had experiments with steam. It had automated machines. Yet the Industrial Revolution didn't happen. Not then, not there. The technology existed, but the conditions required to transform it didn't. But imagine, just for a moment, that someone had taken Hero's experiment further. A stronger boiler, a better pressure vessel, a piston, a crank, a machine capable of continuous mechanical work. Imagine factories appearing, not in 18th century Britain, but in ancient Alexandria. What would the world look like today? The answer may be simpler than we think. Technology doesn't advance simply because someone discovers an idea. It advances when society has the tools, resources, incentives, and institutions to develop that idea. Hero's machine wasn't a failed industrial revolution. It was something more interesting, a glimpse of a technological future that ancient society wasn't ready to build. The ancient world didn't fail to invent the future. It touched the future and then moved in another direction. A bronze sphere spinning on escaping steam. Automatic machines powered by air and water. Mechanical systems that appeared almost alive. The ingredients were there, but the industrial age was still centuries away. And perhaps that's the real lesson of ancient technology. A civilization can discover something long before it has the ability or the reason to transform it. But what if an ancient machine didn't just move? What if it could calculate? What if it could predict the position of the sun, track the moon, and anticipate an eclipse? We have already seen one machine that could do exactly that. But there was another ancient technology, one that reveals just how advanced ancient mathematics and astronomy had become. And this time, the mystery is what the machine could do. It's how they knew what numbers to put inside it. We have seen the machine. We have watched its gears turn. We know that it could calculate astronomical cycles. But there's a question we haven't answered. How did the ancient engineers know what to build? Because gears alone don't create a computer. Someone first had to understand the mathematics. Someone had to observe the sky. Someone had to record the cycles. And someone had to translate those numbers into metal. To the ancient astronomers, the sky wasn't random. The sun followed patterns. The moon followed patterns. Eclipses followed patterns. The planets wander across the heavens, but even their movements could be described mathematically. For centuries, observers have been recording those patterns, night after night, generation after generation. The knowledge inside the mechanism didn't come from one civilization alone. Some of its astronomical cycles were based on Babylonian mathematical astronomy. Greek engineers combined that numerical knowledge with Greek geometry and mechanical craftsmanship. Knowledge traveled, ideas crossed borders, and eventually, mathematics from distant civilizations became bronze gears inside a machine. Imagine the problem. The moon completes one cycle in one period, but another astronomical cycle takes many years. How do you make one wheel represent one cycle, and another wheel represent something completely different? You change their sizes, you change the number of teeth, and you connect them. One rotation becomes another. Mathematics becomes motion. This is the secret of mechanical computation. A gear with 20 teeth connected to a gear with 40 doesn't turn at the same speed. The relationship between them can represent a mathematical ratio. Add more gears, and those ratios can be combined. Suddenly, the machine isn't merely moving, it's calculating. But the moon presented a particularly difficult problem. It doesn't move across the sky at exactly the same apparent speed. Ancient Greek astronomers had mathematical models for this irregular motion, and researchers studying the Antikythera Mechanism found gearing consistent with mechanical representation of that lunar irregularity. Think about what that means. An ancient engineer wasn't simply building a clock. They were mechanizing an astronomical theory. Then came the most dramatic prediction. Eclipses. Ancient astronomers had discovered that eclipses weren't completely random. They followed recurring cycles. And those cycles could be represented mechanically. Turn the mechanism, follow the indicators, and the machine could identify periods when an eclipse was expected. The sky had become a calculation, but the machine wasn't only looking upward. It was also keeping track of time, months, years, lunar cycles, and even the 4-year cycle associated with the ancient Olympic Games. The mechanism connected the movement of the heavens with the rhythm of human civilization. Then researchers uncovered something even more ambitious. Inscriptions on the surviving fragments describe the motions of the planets known to ancient Greek astronomers: Mercury, Venus, Mars, Jupiter, Saturn. A 2021 reconstruction proposed a model of a front display representing the ancient Greek cosmos. But there is an important warning. Much of that front mechanism is missing, so researchers can reconstruct it, but they cannot simply claim they know exactly what the original looked like. But there's a problem. The machine is broken. Only about a third of it survives. What remains has been divided into dozens of fragments. Bronze corroded. Gears disappeared. Inscriptions were damaged. Entire sections are missing. So reconstructing the machine is like solving a puzzle with most of the pieces missing. And then, modern technology did something remarkable. Researchers couldn't simply look through the solid bronze, so they used X-ray computed tomography. Layer by layer, the machine was virtually peeled apart. Hidden gears appeared. Hidden inscriptions emerged. A device that had been silent for 2,000 years began revealing its secrets. Today, researchers often describe the Antikythera Mechanism as the world's oldest known analog computer. Not because it looked like a modern computer. It didn't. There was no screen, no electricity, no processor, no software. Instead, the mathematics was physically built into the machine. And now the mystery becomes almost impossible to ignore. If someone could build this, where did the tradition come from? Who taught the engineer? Who designed the calculations? Who manufactured gears as precise? And where are all the machines that came before it? Because technology this sophisticated usually leaves a trail. But here, the trail almost disappears. Somewhere, there may once have been workshops producing machines like this. Engineers, apprentices, astronomers, metalworkers, mathematicians, a complete technological ecosystem that may have vanished. And when the knowledge disappeared, the machines disappeared with it. Perhaps the greatest lesson of the Antikythera Mechanism isn't that ancient people built a computer. It's that they had already begun doing something we associate with modern civilization. They were taking abstract mathematics and turning it into physical machinery. They were turning ideas into machines. And once humanity learns how to do that, the possibilities become enormous. The Antikythera Mechanism wasn't magic. It wasn't alien technology. And it wasn't proof that ancient civilizations possessed modern computers. It was something more fascinating. A real machine, built by real humans, using mathematics, astronomy, and engineering at a level that still astonishes us. And it leaves us with one uncomfortable thought. What if the greatest ancient technologies aren't the ones we've discovered? What if they're the ones we haven't found yet? Technology isn't always a machine. Sometimes it's the material the machine is made from. Ancient craftsmen learned to manipulate metals, glass, and ceramics in ways that still surprise researchers. They couldn't see atoms. They didn't understand modern chemistry. Yet they discovered something incredibly powerful. Change a recipe, and you can change a material. In ancient India, craftsmen developed a high-carbon steel known as woods. Carefully controlled production created a material prize for its exceptional quality. The steel eventually became associated with the legendary blades of the Middle East. Damascus steel, a material whose distinctive patterns became famous across the ancient world. The remarkable part wasn't the appearance. It was the metallurgy behind it. And then there was Roman glass. Ancient craftsmen could create colored and translucent glass using carefully selected minerals and additives. Some Roman glass objects have survived nearly 2,000 years. But here's the strange part. Ancient glass wasn't simply decorative. Its colors, transparency, durability, and optical properties depended on chemistry that the craftsman could manipulate through experience. The lesson is bigger than steel, bigger than glass. Ancient technology wasn't simply about copying nature. It was about transforming it. Heat, pressure, minerals, metals, fire, water. Ancient craftsmen experimented for generations until nature revealed its secrets, and some of those secrets disappeared with them. We often imagine ancient civilizations surrounded by primitive technology, but look closer and another picture emerges. They were experimenting, refining, measuring, improving. They were engineers, and sometimes their greatest inventions weren't machines at all. They were materials. Materials designed to survive long after their creators were gone. But there is one place where ancient engineering becomes even more extraordinary. Underground, above ground. Cappadocia looks almost peaceful. Strange volcanic towers rise from the landscape. Villages sit quietly between them. But beneath the surface, another world exists. Tunnels, chambers, storage rooms, living spaces, entire underground complexes carved into the soft volcanic rock. Ancient cities beneath the earth. But building underground is one problem. Breathing underground is another. So ancient engineers created vertical ventilation shafts. Some extended deep into the settlement. Fresh air could move downward, while warm air and smoke moved upward. The underground city could breathe. And then came the strangest feature. Massive circular stone doors. They could be rolled into position from inside the tunnels. Once closed, an entire passage could become almost impossible to enter. A city beneath the earth, with its own defensive architecture. These underground cities weren't simply caves. They were systems. Ventilation, water storage, food storage, living areas, workshops, defensive barriers, multiple levels connected by narrow passages. The technology wasn't a single invention. It was a design of an entire underground environment. The deeper we go, the harder it becomes to call ancient technology primitive. They didn't simply build upward. They learned to build downward. They turned mountains into architecture, rock into shelter, and darkness into an entire living environment. But underground cities raise another question. If ancient engineers could build machines, manipulate materials, control water, and construct cities beneath the earth, how many other machines have simply vanished from history? We can study the Antikythera Mechanism, We can examine Roman concrete. We can reconstruct ancient water machines. But these are the survivors, the machines that escape destruction, the fragments that happen to survive. And that creates a disturbing possibility. What about everything else? Machines made from wood, leather, rope, organic materials. Most of them would have disappeared completely. Ancient engineers didn't only build machines that moved. They built machines that appear to act. Mechanical figures, automatic theatrical devices, hidden mechanisms, moving statues, doors that open without anyone touching them. To an audience, it could look like magic, but behind the spectacle was engineering. But machines require something more important than metal: knowledge. A master teaches an apprentice. The apprentice teaches another. Generations refine the technique. Then war comes. A city falls. A workshop burns. An engineer dies without passing on the secret. And suddenly, an entire technology can disappear. So perhaps the mystery isn't how could ancient people build these things? We already know they could. The deeper mystery is how much knowledge disappeared before anyone could preserve it. The Antikythera Mechanism survived by accident. Roman concrete survived because it was buried inside structures. Ancient tech survived because someone copied them. But countless other technologies may have left nothing behind. No machine, no blueprint, no instruction manual, nothing. History doesn't preserve everything. It preserves what survives. And sometimes, survival is nothing more than luck, which means the technologies we know today may represent only the smallest surviving fraction of ancient human ingenuity. And that leaves us with one final question. If ancient civilizations could create technologies centuries ahead of their time, why did so much of that knowledge disappear? We've seen the machines, the gears, the concrete, the hydraulic systems, the steam experiments, the underground cities, the advanced materials. None of them were magic. They were the products of observation, mathematics, experimentation, and generations of human ingenuity. But together, they reveal something much more surprising. Technology doesn't always move forward. Civilizations rise. Knowledge accumulates. Engineers solve problems. New machines appear. And then something changes. A war, a political collapse, an economic transformation, a disaster, or simply the disappearance of the people who understood the technology. Imagine knowing how to build something, but only a handful of people understand how. A machine can survive. A building can survive. A piece of metal can survive. But the knowledge behind it can disappear in a single generation. And once the chain is broken, rebuilding it can take centuries. So perhaps we've been asking the wrong question all along. Not, how could ancient people possibly build these things? But why do we assume they couldn't? They were not less intelligent. They simply lived in a different technological world. They had different tools, different resources, different problems, and different ways of solving them. We like to imagine history as a straight line. Stone, bronze, iron, steam, electricity, computers, artificial intelligence. One invention leading naturally to another. But history is messier. Technology can advance, stop, disappear, and sometimes be rediscovered. Somewhere in the ancient world, there may have been inventions we will never know about. Machines made from materials that decayed. Designs written on manuscripts that burned. Techniques passed from master to apprentice. Until there was no apprentice left, we will never know exactly what was lost. And perhaps that's the most haunting mystery of all. Somewhere in the ancient world, there may have been inventions we will never know about. Machines made from materials that decayed. Designs written on manuscripts that burned. Techniques passed from master to apprentice. Until there was no apprentice left, we will never know exactly what was lost. And perhaps that's the most haunting mystery of all. The Antikythera Mechanism wasn't impossible. Roman concrete wasn't magic. The Baghdad Battery isn't proof of an ancient electrical civilization. Hero's steam machine was an industrial revolution waiting to happen. The underground cities weren't built by beings from another world. They were built by humans. Curious humans, persistent humans, experimental humans. The same kind of humans who are still trying to understand the universe today. And perhaps that's why these discoveries matter. Not because they prove that ancient people were secretly modern. They weren't. They remind us of something much more important. Human ingenuity has no single era. Give people a problem, curiosity, time, and the freedom to experiment, and they will find ways to do things that seem impossible. Thousands of years from now, someone may discover one of our machines, a computer, a spacecraft, a piece of technology buried beneath the earth, and they may look at it and ask, how did they know how to build this? Perhaps that's the real lesson of ancient technology. Every civilization thinks it understands the future, until time reminds us nothing is guaranteed to survive. Not cities, not empires, not machines, not even knowledge. The greatest technology humanity possesses may not be the machines we build. It may be our ability to keep learning. Because the moment we stop passing knowledge forward, the future could become the past. Perhaps ancient technology shouldn't exist. Or perhaps we've simply forgotten what humans are capable of. Thank you for staying with us on this remarkable journey. Kindly subscribe now, because our next documentary will thrill you.